So let me first thank you, the organizers, for inviting me. It's always a pleasure to be here in Paris. And thank you all for making it to the afternoon session. I must say it was hard for me to drag myself out of the French restaurant where I was having a very enjoyable lunch. So the title of this workshop, Big Data, Data Assimilation, and Uncertainty Quantification, I think that fits very well with what we do at ECMWF. So I'm presenting work done by myself. I mean, I lead the data assimilation methodology team at ECMWF, so we'll try to look at the methodological aspects of dealing with big data and uncertainty quantification. And I share the credit and the responsibilities of what I show with a number of colleagues will I mention during the talk. So this is, as Michael said this morning, is a very distinguished audience. Maybe not everybody is an audience with different backgrounds, so not everybody is aware of what ECMWF is. So ECMWF is an organization, European organization, set up in the mid-70s, at a time when European cooperation was a good thing and not a swear word, as it has become more recently in certain quarters. And basically, most of the European nations got together thinking that for doing global NWP, it was better to pool resources together and make a concerted effort instead of going their separate ways. So today, ECMWF is an organization which has 34 members and cooperating states. It has on the order of 350 staff, so this number goes up and down, but mostly over the past few years has gone up. It has got 2 4 teraflops high-performance computers, which when they were installed almost 4 years ago were in the top 10 of the global computers. Now they hardly make it into the top 50. But we are getting new computers relatively soon, hopefully by the middle of next year, and they will be placed here in Bologna, where the new ECMWF data center is being set up. And what we do numerical weather prediction. That's still our core business. But this over the years has, we have increased the scope of our activities to environmental forecasting, climate monitoring, and atmospheric chemistry. So we say we are branching out into a number of similar and related activities. So obviously, I don't have the time to cover more than one aspect, really, of the big data and uncertainty. So I will concentrate mostly on big data. So numerical weather prediction, the way we do it at ECMWF on the scales of hours to seasons, that's what the range of scales that we're looking for, is an initial conditions problem. And typically, we have used 2 sources of information to solve this. The physical understanding that we have of the system, which is encapsulated in the model and its error statistics, and the observations. And the job of data assimilation is to bring together these 2 sources of information in a consistent manner. And over the past few years, and you will hear about this more by an ECMWF colleague later in this workshop, we are trying to do this not only for the atmosphere, but also for the land, the sea, and the ice in a consistent and connected way. So what about the forecast model? The atmospheric forecast model, which is just a representation, we split up the atmosphere in a huge number of grid boxes and then consider interactions about the particles in each of grid box with the others. There's quite a large number of those. Today, we are talking about 6.5 million grid points at each vertical levels, 137 vertical levels. So we are talking all in all about 9 billion. The number of degrees of freedom is order of 9 billion in the current atmospheric model. And as I was saying, over the years, we have been adding other pieces to the puzzle. So it's not only the atmosphere, but the ocean, the sea ice, the land, and all their various interaction with the atmospheric system. And talking about resolution, the situation in 2015 was the grid spacing was around 18 kilometers, and we had 91 vertical levels. So we were talking about 150 million prediction points. The situation now, we're talking about 9-kilometer grid spacing, 137 vertical levels, so they're the order of 1 billion prediction points. And a projection, I mean, obviously, this is more hypothetical because we are not sure yet what kind of computer we will get in Bologna, but we hope to be running at around 5 kilometers grid spacing and increasing the number of vertical level as well to maintain a consistency between horizontal and vertical spacing, which is important from a physical point of view. So this was the question, how big the model and the model state is. Now, what about the observation? Well, the observations, I mean, this is a graph that was provided to me when the ERA 5 reanalysis, which is now being completed, was being put together. And as you can see from the, I mean, at that time, the ERA 5 reanalysis started in 1978. Now it has been extended backward for another 20 years. So it goes even farther back. We're talking about hundreds of thousands of observations in the late 70s. To the current situation, we are tens of millions. And the latest is that we assimilate 35 million observations every 12 hours. This is a number that keeps on going up. And actually, this 35 million observation is actually less than 1/10 of the observation available. So we downsample, we thin them, we superop them quite considerably.
So what are those dips and the gaps?
Well, no, the gaps are just that those parts of the ERA 5 reanalysis were not completed at that time that I got. Now there are no gaps whatsoever. And the dips are where reflect problems in our system. Basically, we didn't receive observations, or some observations were missing, or maybe a satellite or two fell out of the sky. You know, things that happen when you do NWP. So these are big numbers, and what do these big numbers imply in practice for data assimilation methodology? So as most of you are aware, what we do to solve this data assimilation problem is we use a generalized least square approach, which in our community goes under the name of 4D VAR. And that basically means solving a cost function in which we try to blend the information from a short-range forecast here and the information from the latest batch of observation. And the link between model state and observation is through a generalized observation operator, which I call G, which is a composition of the standard observation operator plus the model evolution, because we are solving for the state at the initial time of the window, so we need to bring forward this state. And the claim to optimality of this system is that for linear observation operator and models, the minimization of one is effectively gives you the fixed lag Kalman-Smoother solution. So that's what we are aiming for. Unfortunately, this equation as it is cannot be solved in practice for our system, and this was realized very early on by, for example, Philippe Courtier was one of the person who actually spearheaded the use of 4D VAR in operations. And I can think of at least 3 reasons why the standard 4D VAR formulation cannot be used directly. First, the dimension of the error covariance is involved. So we're talking with huge matrices. Second, the fact that if you want to efficiently solve this kind of cost function, you require repeated gradient computation, which means repeated evaluation of the forecast model and its adjoint, and that's very costly. And finally, the fact that the use of a nonlinear generalized observation operator results in non-convex cost function. And that makes finding the global minimum very difficult. So, approximation. One needs to do approximation to solve this kind of problem. And one first starts making approximations with the error covariances in play. So first we make an approximation of this quantity here, which is the background error covariance. And the approximation that we make is that we represent it in wavelet space. And not only that, but we assume a diagonal representation of this matrix in wavelet space. What this means in practice is that we are assuming the local isotropy of the correlation tensor. So our error covariances, background error covariances, are locally isotropic. And then we do sparse approximation of the observation error covariances. And in particular, we, at the moment at least, we zero out the horizontal correlations. We keep vertical and spectral correlations, spectral in observation space correlation, some of those, but horizontally, we just assume the observations are uncorrelated, or they're errors. Then we have the second and third problems, the fact that the most efficient solvers require repeated gradient computation and the nonlinearity. And these are solved going through an incremental formulation of 4D var. And the whole idea here is to approximate the nonlinear cost function as a sequence of quadratic cost functions of initial perturbations around successive trajectories, which hopefully are more accurate and closer to the truth. So this second important approximation allows us to go around the problems number 2 and number 3, because first, the linearized models used in the cost function can be lower resolution than the full nonlinear system. So they basically mean, and to put some numbers now, the linearized models now run at 50 kilometer resolution, while the nonlinear model is run at 9 kilometer resolution. So the effective resolution of the analysis increments that we had is 50 kilometers, not 9 kilometer. And secondly, we have quadratic cost functions, so they're strictly convex. So we can use conjugate gradient or its variants to get efficient solution. So this is basically, in a nutshell, incremental 4D var, which has been the workhorse of ECMWF data assimilation for the past 20 years.
So it does guarantee a global minimum, but that global minimum can be fragile to the observations, right? There will only be one minimum, but if you get one of delta XA, 1 or 2, away from the true minimum, if there is one, you'll still have a global minimum, but it won't be the point you're looking for.
That's a possibility in theory. In practice, no. In practice, it doesn't work like that. And I think, most of the reason is that we have so many observations, so you are sampling very accurately, so that you are really very rarely moving away from a system which has an approximately linear evolution. But I will get back to this point. So what is the problem with this, looking forward towards even bigger data, even higher resolution computers, even more observations? So first, despite all these simplifications, incremental 4D var is a very expensive algorithm. So when we do a 4D var, it costs more than a 10-day forecast at full resolution. And it takes, well, maybe a bit less than 1 hour, but not much less than 1 hour over 12,000 cores. This is what we're using at the moment. So it's very computationally intensive. And the second thing, even more problematic, is this is an intrinsically sequential algorithm. So say, let's assume that we are here in one of these black quadratic cost function. The way to find the solution of this cost function is sequential. It goes through a series of operations that one must be done one after the other. They cannot be parallelized in time. And on top of that, the outer loop, so the relinearizations that we do in this process, so basically going from one of this black cost function to the next, this also needs to be done in practice, because we need to compute, basically solve one of these problems, find a new starting point, compute a new updated trajectory around the new starting point, and iterate. And we are in a situation that the nonlinearities in the problem are increasing, both in the model and in the observations. And I will show an example here for, this is a measure of nonlinearity in observation space. It's not really important what it is, but what you can see here is that for standard Radisson temperature, this measure tells you that it is a very linear type of observation source. Once you start putting in humidity observation, you can see that you're starting deviating from this linearity. When you start having observations that are sensitive to cloud liquid water, then you can see that the linearity assumption starts to break. And if you can just imagine that people are now working to assimilating lightning imagers observation, you can imagine how this nonlinearity problem is going to become more and more important. And also, the nonlinearity of the model, where this is shown here by showing basically the magnitude of the difference when you integrate, do a nonlinear integration from a state and do the same linear integration from the same state plus the linearized model of the perturbations. This has actually gone up over the years. It used to be much less of a problem 10 years ago, and it's gone up. And it's mostly because the model has become higher resolution and less diffusive than it used to be. So the nonlinearity of the model has a bearing.
But in this case, the linearized model is not a lower resolution version of it.
No, these are the same resolution, yes. So it's just an intrinsic measure of how much the linearized model diverge. So what can we do about this? Well, I'll present now a couple of ideas. One that has already been implemented, and another one that we are working on. So the first one is from intermittent to continuous DA. So I've heard people talk about continuous DA already here. So these are our take on continuous data assimilation. So the idea comes from the fact that, as you can see, I mean, this is a timeline of how we get the observations over time. So this is for radiosondes, and you can see that you get every 12 hours, you get this timeline. This is for radiances, and you can see more or less spikes over time. This is for aircraft observations. So basically what happens with observation is it's not like in the old time that we used to get observations of synoptica. Now 99% of the observations, it's a continuous flow. On the other end, well, now it says, here it says the current, but actually it was the previous operational, the previous, as in previous of June 2019. So basically what we are doing is we concentrate the analysis computations into two windows over the day. So this 12-hour window, and then the following 12-hour window, and this is where we cycle the information. But also we have two additional smaller, we used to have two additional smaller data assimilation windows, only 6 hours, because people couldn't wait that much time to get the 12-hour assimilation window, because in this 12-hour assimilation window, we were waiting for observation, for all available observation to arrive. So we were starting the assimilation window 5 hours after the nominal time. And that's too long a time. The focus then becomes old, and people say, okay, now we want a fresher focus with new initial conditions. So we do this, basically, this post-processing smaller 6-hour data assimilation window to actually run the forecast, even though not all the observations that are relevant have arrived. So that basically puts us in a conundrum, because if we wait longer for the observations to arrive, then we have less time to actually do the assimilation, where we need to settle with a simpler assimilation system. If we start doing the assimilation, the ensemble forecast, well, it requires another discussion. But in principle, yes. If we start doing the assimilation earlier, it's fine, but we lose observation. So this idea that we had was simply to exploit the inner outer loop setup of 4D VAR doing this. So this was the previous configuration. So 1, 2, 3 are the outer loop relinearization. So you start here, you do a minimization. In here you relinearize, second minimization, 3 relinearize, and then do another minimization. So the idea was, okay, but can we actually use during the second or third minimization the observations that have arrived in the meantime? You can imagine that each one of these takes around 20 minutes to run on supercomputer. So basically in this way. And then once you made this step, then you can say, okay, but I can actually start earlier. It doesn't really matter if I start earlier. I can put other outer loops because I'm not losing observational information on this. So this was, I mean, something simple, but very effective because, I mean, this is just show how many observations you get even in those hours in which 4dvar is running. And you can see that they are globally, and they are fresher observations usually because when they arrive late, they are in the second part of the window, so they usually have more influence on the initial conditions. And so what you get in the end is, in terms of forecast skill, is this very blue plots which show improvements. And improvements is about 2 to 3 hours extended predictability, which doesn't seem much, but I mean, in the 10 years that I've been at ECMWF, it is the single largest forecasting impact that you have seen of anything that we have done. And actually, this thing can be, you can imagine carrying it forward. So one can actually imagine to restructure the whole system by having basically this 6-hour assimilation window and then moving forward the assimilation window in time, 8 hours, 10 hours, and each time adding new observations that have come in the system. So this is a direction in which we are going. The other big idea is parallel minimization. So we haven't touched the issue of minimization in itself, but the minimization inside the linearized cost function, so the quadratic cost function, that is still a sequential problem. So one idea is to introduce parallelism in the time domain, which means subdividing the assimilation window in smaller time windows and then try to solve 4dvar in parallel in this assimilation window. And this can be implemented both as a strong constraint 4dvar or a weak constraint 4dvar and leads to a modified cost function of this form. So I will not discuss this in any detail. I will just say that this is a very attractive idea, but there are, so far, unresolved issue of convergence of the associated Lagrangian problem. So to actually solve this problem, one must project it into a Lagrangian multiplier idea. But when one tries to solve the associated Lagrangian problem, you cannot guarantee uniform convergence. And that's obviously problematic for us because it means that operationally we are not sure when we can stop the minimization. Another idea, and this has been mentioned this morning already, is to try to induce parallelism through stochastic techniques. And one idea is the randomized SVD approach. So this has already been described, so I will not go into detail. I would say in terms of randomized SVD approach, I mean, the good thing is that obviously there are parallel application of the TL and adjoint models, which should be done once or twice, and this can be done completely in parallel, so this is very promising for us. On the other hand, something that has been mentioned before, convergence speed depends on the characteristic of the Hessian of the cost function, and in the case of the atmospheric problem that we have, this Hessian doesn't appear to fall off as fast as it should. So in the end, since this is a method that doesn't use gradient information, we are, at the moment, we currently think the hybrid methods, which take some ideas from the randomized SVD, but also use some kind of gradient information, having a mixture of an hybridization of those methods could be the most effective way of tackling the problem. And this is the direction in which we are going. So conclusions. So what I've discussed today, I think I talked a bit about big data in data assimilation for NWP, and this is as big a big data problem as you can find, actually. we have been using variational methods for the past 20 years, but these are becoming more difficult because of increasing model resolution, observation, etc. So there is clearly a push towards finding a more scalable algorithmic solution, and I've shown you some ideas in this context. What I would also like to discuss is efficient estimation of uncertainty, so the ensemble aspect. I just touched a little bit on talking about randomized SVD. Randomized SVD, one of the good things is that it allows for basically getting samples of the posterior error covariance matrix, and that could potentially be interesting in terms of ensemble data assimilation. This is something that we will look at too. And then the elephant in the room, the impact on data assimilation of potentially disrupting new technologies such as deep learning. I mean, there are many perspectives that one can take on deep learning. I mean, I'll throw in one. As I said at the beginning, data assimilation has traditionally been seen as the way to blend two sources of information. One, a model through the short-range forecast, and then the latest batch of observations. On the other hand, we have now a huge archive, I'm talking about petabytes, of high-resolution Earth system forecasts and analysis, and also a vast archive of quality control observations. So it's clear that there is information in that archive, and it's clear that deep learning and machine learning in general can help us get some of these ideas. And I think, I mean, we as a community need to find the ways to exploit this additional source of information effectively. So on this subject, we'll soon start a collaboration with Marc Bouquet's group looking at specific aspects of model error and model identification. But I mean, if you have ideas and if you want to set up a project and you're looking for this kind of vast archive of information, then let us know, because we are also very interested. Thank you very much.
Thank you very much, Massimo. That was very instructive to know what the real stuff looks like. Yeah, if I may, I mean, instead of making 4D VAR more and more sequential, what about giving up on 4D VAR and really doing sequential? You know? I mean, I remember in 1980 when I talked at the first seminar on data assimilation at the European Center, I was laughed off the stage when I talked about sequential estimation, because I was told that that could never be done. Well, never has come.
Well, I guess, I mean, it's a question on how to employ resources. I mean, if you want to do, I mean, sequential estimation, ensemble Kalman filtering, I mean, you have a very parallel problem, but effectively you need to use a lot of ensemble members. So you're filling up the machine with your model in other ways than you do with 4D VAR. One thing that I can say, however, is something that people, I mean, and if you don't work in an NWP center, you're not really aware of this issue. There are like 100 or so people who actively develop the model and the assimilation at each time. And each one of those people needs to execute experiments, to run experiments on the supercomputer. So one thing is to run one 4D VAR experiment at a reduced resolution. Even at the same reduced resolution, imagine if you have to run ensembles or particle filters, etc., together. So it's a real problem of what you can afford in terms of operational development.
Yeah, but can you afford to remain stuck in a decision that was taken, as you put it, 20 years ago? I mean, I used to, in my early days, I used to interact quite a bit with people who were doing just those things. And, anyhow, now there are just many more of them. Okay, sorry for, Olivier. He is responsible for Philippe Courtier.
You sent him there.
Nothing to do with variational, sequential, or relational. In fact, not directly related to your talk, which was concentrated on computational aspects. But concerning weak constraint assimilation, what is the situation at ECMWF now? Do you have any form of weak constraint assimilation, and which one?
Well, actually, this is a very recent result that I didn't talk about today, but there are 2 papers on this under review. So maybe somebody in the audience could actually speed things up a bit. But effectively, what we have is we have the forcing formulation of weak constraint for Diva, so the ones with model errors, and effectively a constant model error throughout the window, that now finally works, and it actually is able to debias the stratospheric analysis. And I think, it's possibly it's the first time that weak constraint for Diva has been shown to do, or operationally has been shown to actually be able to do something useful. So
It's not weak constraint, right? Not really, because you estimate in one field, one statement.
Sorry. You need to be recorded, Peter. You can't just talk like that.
If you're estimating a bias, that's not really weak constraint, is it?
Well, you need to make assumptions at some point. This is like, there are a lot of assumptions, but actually the problem was, in the previous version of weak constraint for Diva, was that, people were not clear what they were looking after, they were looking to correct. Were they looking to correct the model biases, meaning, biases here just in the sense of error that evolve slowly over 12 hours, not biases, seasonal bias, or they were looking to correct for, say, stochastic model error. If you're trying to do both, our experience has been you fail. If you actually let the B part of the cost function take care of those stochastic errors and the weak constraint part, the model error part, take care of the biases, then they can live together peacefully.
Okay, so now we know that DA methodology development at the European Center is in good hands. Thank you very much.